Testing, testing. Hello.
Hello.
Hi. How are you?
Paul.
Okay. So the meeting has started.
Yeah, the meeting started a couple of 5 minutes ago. We've people have only just started coming now. There's another guy, Thomas Stephen, who wants to join. So we'll see. He can join, and if he's not interested, then he can leave. You know, he's been following the Facebook comments for a while. David said he's voice only to begin with.
Uh-huh.
And I think Justin said last week that he wouldn't come this week.
Okay.
Facebook page, he may have done a typo saying that he would come, so I'm not sure if he's coming. Can you hear us, David?
I don't see David's window.
I wasn't expecting
Michael, it's
the meeting
Michael.
to be so soon myself. I guess I keep getting mixed up. I thought 4 o'clock Eastern time was same as 8 o'clock Greenwich Mean Time, but I messed that up. Thanks for the reminder.
Okay. Anyway, well, I can start by saying that I've done a bit of work with the code using C++. Oh, David Johnson just said he'll connect in half an hour. So let me just. So this is the C++ code. By the way, Paul, did you make any progress with the so-called black hole images?
Oh, yeah, I managed to contact an astronomer in Arizona who's with the team. And she explained to me the problem is that they haven't been able to create an image yet because Sagittarius A is flaring on time scale of 10 minutes. And they have to observe over hours. And so they need a steady image over that period to create an image. So they need to compensate for the flaring. So they have to create a computer model to take care of that. And I don't think they're equipped. They probably have to bring in experts to do that. And they weren't prepared. So they were caught with their pants down, so to speak.
All right.
Might be another month.
I noticed on the Physics World magazine that I get, it was on the front cover of the most recent one, the image.
Of what? Of the M81? M87 or something?
Let me see, that's the, I'll take it out of the package. That's the physics.
Can you hold it higher up?
Yeah. So
a little higher. Yeah. Yeah, that's the one that I reported about that on my website. So that it's really too far away to really say much about black holes. The fact that it's black in the middle doesn't mean it's a black hole. It's just probably the way that the black hole or the supermassive core is warping the light, you know. I think we really have to wait for the Sagittarius A image.
Okay. Well, what I can do to start with is just show you this is what I plotted out of the Crank-Nicholson solver, and it's showing it's at time interval 10. So the whole simulation is up to 100 time units, and this plot was at time unit 10, so it was a 10th the way through the simulation.
It looks sort of like what Matt developed,
yeah.
The same form.
So let me just have a look at the.
You can put the X on a lower scale, so it's not so long. you know, put it out like 1/10
Yeah,
scale.
yeah. From there to say there. To there. I was looking at the Crank-Nicholson solver again because it seemed to be a bit more complex than I first thought looking at it. So this is the one on Wikipedia. It seems to be saying that it's like the trapezoidal rule, and which is relatively straightforward. It's like a his order was based on the trapezoid method. Get it down here. Where is it now? Here it is. So the trapezoid rule says based on the trapezoidal rule, which is basically can you see that diagram there? So it's basically taking 2 points, these lengths here and this length here, and then well, basically the area of a trapezoid under the curve, and then just summing it up for all the points. So it's taking that area, that area, that area. So, and then summing it up to get the area under the curve. So that's basically, so it's based on the trapezoid rule, but it's what I'm understanding, it's more complicated. It looks like, from what I'm seeing at the moment, it looks like a fair bit more complicated. What I'm thinking of is something more like this here. Can you see that, Justin? So it's looking like it's kind of like this kind of thing with matrices like this. This is what I'm thinking now.
Yeah,
I'm not sure if Matt has made it as complicated as this, but that's an example from Wikipedia.
That's standard technique. That's standard linear algebra technique for simplifying the problem.
Okay, so so basically what I've done is I've gone into code, and I've gone up to the top and taken say we've got time equals 100 here. I've changed that to time equals 10,
Okay.
and got out. So
you're asking, is that extra complex? No, that's pretty standard.
that's very straightforward. I was just checking.
You go to a numerical methods book. You go to a using numerical methods to solve linear matrices, systems of matrices, linear algebra systems of matrices. That's what you're going to see. It takes a little time to get it. It's not too sophisticated, like sophomore, junior level, but you do have to spend some time to learn it or to review it if you haven't gone over it in a long time. Because
you're talking about the Crank-Nicholson solver, Justin.
Yeah, I know you're talking about that, but you're using the matrices techniques is what you were looking at.
Yeah.
And that's a whole class of techniques to use. So they're using that within the Crank-Nicholson algorithm. That's some of the tools, the base tools they're working at. So if you want to try and understand how all those things work, there's a lot of literature on it, on the linear algebra part, and then extending it to the more advanced Crank-Nicholson. That's that's one thing that you could look at. But just looking at how to solve linear matrices, the system's linear matrices with numerical methods, that's how you can see how these directly correlate to the program code.
And what I was thinking they're showing out here, they're showing 11 to 34. I think that's they're just showing one segment. So they're not showing all of it there. That's what's into.
Yeah, those are indices in the matrix, I believe. So it's like column 1, row 1, column 1, row 2, column 1, row 3, column 1, row 4, and then you go to the next row. I think it's row column first. Okay, so it's the first one's the row and the second one's the column.
And you can see here. So basically, what they've done here, from what I understood here, is they've taken a partial differential equation.
Correct. And converted it into linear matrix.
Divided it up they pieced it apart to be processed by the Crank-Nicholson solver.
Yeah, they turned it into a linear matrix, and then they solve they use a standard technique to solve the linear matrix, a set of equations. So it's a linear matrix that describes the system's equations.
This is 1D.
That's 1D, yeah.
I guess it gets pretty complicated, go to 2D.
They've got an example of 2D here. I didn't look at it very much, the 2D diffusion. This is the way it's kind of like let's see, that's the way it's, and then they seem to split it up like this. So first of all, they talk about they describe it in these terms here. My mouse isn't working. Describe it in these terms here, and then that term there, this term here, and then they divide it up into that term there. So I found about 5 different sites that looked reasonably interesting on just talking through the stepping through and deriving and giving examples of the Crank-Nicholson solver. I had a little look. I've got a brother-in-law who's prepared to help me out, to help fund some of what I'm doing. So he's hopefully going to put some money in my bank soon, and I'll be able to buy the Mathematica, the hobby version, which is £225, more like $250, $260. So eventually, I should have that soon, and then I'll be able to see whether Mathematica, have a go with Mathematica and see what I can do there. Apparently, Michael said, if you remember Michael, that Matt said he preferred the Mathematica method of all the different programming tools. So anyway, that's that one for 10 seconds. And then this one was what I did down here for that's the 100. That's 100 seconds. That's what it looks like. We've got the red is the exons, yellow, green is the geons, and black is the yons. There's a little issue with the what do you call it? What do they call this? This bit here. I had to paste it in by hand because sorry,
Would
Paul?
they give you a discount if you said that I referred you, because I had purchased it? I didn't really use it much. But maybe I think they might give some discount if you were referred from somebody that had it, right?
I think you could just transfer the license to him if you want to. I think you just
Could I?
I believe so, as long as he uses the version that you have as opposed to the new version. Yes, that's standard practice to sell a license or share or give a license away.
Even if it's from Mac to Linux, Justin?
Oh no. That won't. They have simulators for yeah, I don't know, for Mac to Linux. That's a challenge. So
Mine is for Mac.
Your Mac, okay.
You want me to contact them and see if they can transfer the license?
No, he'd have to put it on a Mac, and he doesn't have a Mac, so.
Oh, okay.
So anyway, I had a look in what's the jig? This is the GitHub page that I've linked with David Johnson's, and here this here is the MATLAB code. So that's where I call the G, X, and Y that I plot that I've got the file from C++, and down here plotting. And I was having a little look to see if I could do a video of the Crank-Nicholson of this developing. So I'm not sure how well I'll be able to do that. I'll have a little go at it. It's a bit more tricky using Octave than MATLAB, because MATLAB is professional code. It costs, if you're outside of university, it costs about I don't know, I may be wrong about this, something like 1,000 or 2,000 pounds to buy, and they've got all the sort of professional code. So Octave is a kind of hybrid of open source hybrid of MATLAB, and Octave you can do a fair bit with it, but it can't do all the fancy stuff that MATLAB can do. So I can't. It's not that straightforward to produce an animation, say this, but I'll have a look at it and see what I can do. It may be best to go back to look at the EDT stepper and see how Matt's done the animation in there, and then transfer it over to this.
So what are you trying to get out of it from an animation perspective? I threw some notes up in Facebook on how to.
Well, if we can do from time 0 to time 100,
yeah,
it's in sort of steps of.
Okay, so how I described it is look at that, what you have there from a diagram perspective, and think of turning it on its side. Okay, and then think of having a whole bunch of those over different time periods. Okay, so time 0, it's going to be a little, pretty much flat, and then those waves are going to start to evolve over the 800 time periods that we have here, I believe. No, it was 100 time periods, I think. I forget. So you can actually do that, and I actually showed you in the code on Facebook where you could take, because you basically are outputting all of this data at the very end. You could output this data at every increment if you just move this code that you used to generate this, and you moved it inside of the increments, and you just put it there. Then you could actually get all of these different time slices, and then you can just have them one after another, so that you could have a 3-dimensional view, and you could use GNU plot or Octave plot or whichever one you're using to actually look at that. From a 3-dimensional perspective. It just takes a little bit of understanding of how GNU plot works and how you need to, the format of the data that you're putting out. But where you put it out and what you put out is very clear. What you put out is what you put out at the very, that double for loop at the end. I have some notes in Facebook I put it on. What you put, that's where you're putting it out and how you're putting it out. But you just take that loop and you put it in for every increment. That's the triple for loop. If you put, I think it's not the triple for loop. It's just in the increment. Yeah, if you look down at the bottom of your code, and you can see your double for loop, where you're generating all that output at the very bottom. It's a double for loop.
Yeah, that's the double for loop there.
Okay, so you just copy that code or your function, what have you, and you move it up to where scroll up, see that next iteration function? You just put it in that next iteration function. So you just scroll up and where that next iteration function is, and you put it in here so that you would be putting it out. Now, I do not know the format of the plotter of what it's expecting, but what you put out and where you put it out is straight, it's straightforward. So I'd have to look at the GNU plot or Octave or whichever one you're using to see the format that the data needs to be in. Because what you're pulling in data for a 2-dimensional plot, but now you need to understand how to pull in data for a 3-dimensional plot, because each one of these iterations that you're going to be putting out is going to be the entire data set for a 2D slice over. So here you've got the time. Here's your end picture where you've got all these waves. I'll just put all these. You got these waves over here, and so now you're going to be, for each iteration, you're going to be putting out those. Well, it's first going to be a line, and then it's going to slowly merge into a few waves, and the waves are going to get bigger and bigger and bigger. At the end, they're going to be like this. So you're going to get all these 2D slices all the way up to here. Okay, so it's going to start as a line, then they're going to get to be, some smaller waves, and they're going to get to be bigger waves, and that's going to be your end iteration. You're just printing out this end iteration, but you could, for each iteration, and that's why I say put it in this next iteration function. You could be putting out that picture, that full picture all the way through. So you have to look at,
also you can change it down here, Justin, just down here, where I think you can change that. You can divide that.
No, the problem is
you can divide that into.
you're looking at this data, the values of MX, they keep changing. In each iteration, they change. So you have to print it out as you're doing the iterations. So for each iteration, the values in that array are changing. So you have to put the same code. You just have to take this, these 2 for loops and put them up there. You can put it into a function call if you want.
Okay, David, just connected now.
David.
Hi, David.
Hello.
So what I saw is that this is the reaction that's being called. That's being called in the Crank-Nicolson solver. So this
Right. So that does all the equations, and at each iteration, it's going to be putting values in the the MX array, and so you can print it out at once you're done with the iteration. So it'll be at the end of the iteration code, at that end of that iteration.
I noticed that this here is very similar to the equation 13. See. Can you see that? So it's very similar to equation 13 there, except it doesn't have the chi function, which is shown in it was shown there. It doesn't have equation 13 doesn't have that, but that code in the EG separate is very similar to this, except it's got a plus and minus 3 somewhere. So it's very, very similar to that, except it doesn't show these bits here. It doesn't show these bits here. They seem to be solved in the Crank-Nicolson solver. So the Crank-Nicolson solver. This term here, D, comes up here is where the you can see up here at the top where D is this, and this is where the dx comes in. So the dx and the dy are multiplied there. So in terms of the model G, that's where the dx is, the dy. So it seems that the Crank-Nicolson solver. So if you think of it as an integral, you want to solve for phi x. Therefore, as for a straight sort of naive integral, you bring the t up here and then take the integration. But it's not straightforward as an ordinary integral, because you've got these terms here that you need to work out as well. That you can't just bring the t up and take an integral. It's a partial differential solution, which makes the Crank-Nicolson solver more sophisticated than, say, the trapezoid rule. So these are some links on the internet where they describe about so going to different links describing the Crank-Nicolson solver will help to understand it better, getting it explained by someone different, a different author. But I think what I was understanding, I thought one really has to understand what the Crank-Nicolson solver is doing. One has to understand the details of what it's doing. Then the code becomes more easy to understand. One understands the Crank-Nicolson solver more in depth and properly, then that code will be more this code will be more straightforward to understand. If you don't understand it very well, it's not going to be more tricky to understand the code. So what do you think, Justin? Do you think Matt Pulver is using something similar to this?
Yeah, those are the standard techniques, and I'm certain that there's linear algebra being used across the spectrum. I think understanding the basics of numerical analysis, a good book on numerical analysis, which is going to cover some of this linear algebra and how to solve linear algebra, and then how to convert systems of equations, of partial differential equations, into linear matrices. I think that's a basic part of this set of techniques from my recollection of my numerical analysis.
And we notice also that this is a 12. This is a 12 by 12, and I think it's also not the whole thing, because you can count these 1, 2, 3 goes to 12, and that's got 34 altogether. He's saying there, please note this is a 12 times 12 array. And
Yeah.
I
Okay.
think
So
it's even bigger than that.
you're using the term 12, but it's really, one row by 4 columns, and it's 3 rows by 4 columns. So when you use 3, 4, it's a little misleading. You might want to say 3, 4 instead of 34.
More like 34 by 34.
It's not 34 things. It's 3, 4. They're describing the matrix. Okay, that's got how many rows and how many columns.
Well, he's saying that please note that the sizes of AA and BB are 12 times 12. So they're not that A there is that bit there, and that AA2 is this AA here.
Okay.
Okay, so what do we want to do? Do we want to talk about some, because that's just the
Okay.
technicalities.
So yes, exactly how you described it is a 12 by 12 matrix. That makes a lot of sense because so yes, that's the correct definition.
I was just thinking, instead of talking about the details of the code, do people want to talk about some other things related to what we're doing? Paul or David?
Okay, I'll let you guys go first. I got a couple of things, including I just went to a conference and one of the presentations I saw was on the black hole photos, so I can provide some details on that. And they are out, and I put a link in Facebook to what the photos actually look like, as opposed to some of the non-clear pictures.
Photo of which? Of the M81?
87? Yeah.
87?
Yeah, if you want me to share, I can share.
I have that on my website.
Justin, I'll stop sharing.
Okay, so, yeah, what you had is a pixelated, something that's pixelated. It's not that clear. The actual photos are more fuzzy than what you had on your website. You had a bit of a pixelated one, which sort of made things a little clearer because they didn't use as many pixels. I'll show you what the photos that they showed, and there's actually 4 different photos that they then smoothed together. But they were all kind of fuzzy. So I'll go ahead and see if I can share here. Share.
You have a link. I'd be interested in.
Yeah, give me a second to. Yes, I did put some links in Facebook so you can see them in there. I just put them in 10 minutes ago. I just got back and I figured you guys would be interested.
Yeah, I also did something. I started to rewrite this in JavaScript because that fits me better. And I'm mostly through there. And I sent the link also to that thing I did in 2014 that could be reused, a lot of that. So I'm just basically putting in this equation in an already existing solver. And that's 2-dimensional. So maybe we need to do something, maybe I need to do something with that. But to go to 3 dimensions makes it so much slower.
Okay, so I don't know if you can see my screen or not.
Yes.
Okay, so the thing is, what you had a shrunk down picture. So because of that, everything got sort of cleaned up. This is really what it looks like. It's more dirty. There's more fuzz in there. There's more gray in the middle.
Right. Okay.
And you can see
put that picture up then, the one you got.
This is, and there's several papers. This is one of the, I put a link in there that's got numerous ones, and I think that's one of the ones that has the picture. There was actually a sequence of 4 pictures that he had in his presentation. Well, that's not one of them. I think here's another, same picture. You can see that there's more fuzz there. Notice it's very bright down here. That was pretty constant among the 4 pictures that, okay, so they had 4 different pictures that were done 4 different days. And this is cycling around really quickly, okay? The rotation is 4 to 30 days. And so this is continually changing, this part here. I don't know if you can see my magnifying glass going over it. I don't know if the Zoom is capturing that or not. But this pattern was changing. It was bright on the bottom here, but that pattern kept changing among the 4 different photos. And I haven't located, because he did a presentation, and this is the links he gave, but I don't see his presentation in the links. So, or the sequence of 4 photos. I'm just seeing, I think, the one that blended them all together. But you could see the differentiation between them, which was more information. So you can see there's like 4 or 5 that have this picture. The one that you had was too clear in the middle, but the reason why that happened, and we talked about it in the conference, I asked the question, and they said, well, that was just a shrunk down picture, and so because of that.
Okay, but what is the relevance for Model G for this picture?
I think that's a Paul question.
It's just I'm predicting they should find a mother star. They shouldn't find a black hole. In my opinion, that's too far away to really see much. That emission is from the gas around the core. The actual radiation, they can't see that because it's in the ultraviolet, and actually X-ray and gamma ray region. Those cores, they're so hot they can't radiate at that wavelength. It's what you're seeing is just the cosmic rays illuminating gas around the core.
Okay.
Okay. So I don't know what, you've got this dearth here in the middle, but there's no gas there. So just the fact, okay, so they used, the algorithms are fairly complex.
The reason there's no gas is because it's being pushed out by the wind.
Well, okay, so that's you might call it that, but the thing is, there's this entire area out here that should be that has light also. I mean, this is they in order to get this one square, and because this is actually appearing in a whole blob of light that's all the way around it, and they didn't describe how. They described how this square was taken out. They didn't really describe how.
In other words, they cut that out and stick it in a black background, right?
Yeah, that's really what it appeared to be happening, but that was not clear. They talked about the algorithm of selecting the square to focus in on. So there's a whole slew of different techniques to use, and I can spend some time on going over it. From what I recall, but it would take some time, and I would be kind of vague. It'd probably be better if I were to read over this and see if I can find more of his notes, or ask him for more of his notes, because he had more notes than what's just shown in all these links. And he does have a contact information, so the guy who reviewed it.
Okay. Justin, were you there when I said that I spoke with an astronomer in Arizona, and they told me why the Sagittarius A star image was delayed?
Okay, why did he say that? Because we talked about that in the meeting too.
Yeah, it's due to the flaring. It flares on a 10-minute time scale, and they're observing over hours. So they have no way yet to correct for the flaring. They have to, if it was constant, they could have made an image. But until they get a program that corrects for the flaring, they won't be able to put out an image.
Yeah, there was, and I don't remember details, there was this image when they talked about Sagittarius, in that its rotation was not the 4 to 30 days. It was, I think, rotating much too fast, or so they couldn't get a constant image. Because of the rotation, but here they had a rotation over 4 to 30 days, and they took 4 photos.
Are you sure?
8 different times.
Rotation. I heard that there was only a blue shift and not a red shift or something like that. So how do they know it's rotation? They're assuming that, I think, right?
I heard you saying,
You are
Paul,
absolutely correct. I did note that when I was listening to the presentation.
I heard
So-
you say once, Paul, that they're so far away you can't really tell
Yeah.
these objects.
How they blended it was a fairly complex algorithm, because the data that they were actually pulling in from those telescopes was so fine and so thin, they had to use very extensive interpretation algorithms, and they had to spend quite a bit of time making those interpretation algorithms as generic as possible and based upon as generic information as possible. And they had to see if you know, hey, if we base it upon 2 dots, what comes out of it? If we base it on a disk, what comes out of it? If we base it on a crescent, what comes out of it? If we base it on a ring, what comes out of it? And so they did that, and they got 4 different photos from 4 different groups, based upon another algorithm of and so they had these bases, and they had very different bases, and each one of the bases came up with the same picture. Even though they had 2 dots, or they had a crescent, or they had and this is what they described, or a ring or a disc, it still came out as the same, very, very close to the same picture. And then within that, they each one used 4 different, or 8, 4 different groups did it with 4 different algorithms, but with I think the 4 different bases, and they still came up with pictures that looked very similar to each other, and they worked on different days, so they each one had a picture of a different day, and then they blended them together in what was seen there. And then they had some algorithms to similarly pull out the region of data that they were going to apply this to. So these were all very fine things. You know, the reason why they had some confidence is because they had very different algorithms trying to do the same thing, and they came up with similar results, even though they used different bases to do everything on. So different algorithms, different bases, yet they were getting the same result. So it was highly interpreted, and it was automated interpreted, and the objective interpretation as best as they could get it. Of course, the newspaper, you know, how they're presenting it here, you know, because I saw the picture that they took this out of, and the whole thing was lit up. And I say, well, where's all the other lit up stuff? And they said, well, you know, they just selected one piece, and it's like,
Reminds me of the Higgs boson when they found that.
They want to make it look simple for the public.
Yeah.
Try to convince the public that they found something. Yeah.
I know. So your interpretation is that they're going to find a mother star?
Yeah, well, they won't find anything looking at this. You know, it's just too far away, I think. And they're looking in millimeter wavelengths.
Okay, yeah, they didn't talk too much about the wavelengths they were looking at, but I noticed that they've got a fuzz here, but there was light coming out here. Okay, you can see that's lit compared to the black behind it.
Right.
So, you know, somebody else asked, hey, so does this prove black holes? And they said no. This is a very clear answer.
Is this a black hole in the center of the galaxy?
No, okay, that would be Sagittarius A. This is a whole galaxy that's out there, M87. It's 1,000 times farther.
It's in Virgo cluster.
Yeah, it's 1,000 times farther than
2,000.
Okay,
2,000.
I'm fuzzing, you know, 1,000, 2,000. It's okay. Yeah, you're right. It's 1,000 in the thousands, 3 orders of magnitude farther, and 3 orders of magnitude bigger, according to their estimates, than the center of our galaxy. So it's in 3 and 3. So it proportionally you would think it was the same, but there might be other things, so 3 times farther, but 3 orders of magnitude farther and 3 orders of magnitude larger.
More
So
more warped is the way to put it.
I don't know what to go with this. This is all really far, you could say it's like looking at the number of angels on the head of a pin. I mean, they're really stretching the data pull and analysis.
Well, they have to, give the public something to explain why they're spending all this money for this effort.
There you go.
Yeah, it was about 20 to 40 million dollars they spent on it.
Hmm.
Yeah.
They would save more money if they went to a Model G, Paul.
Yeah, I'm trying to look for it. I'll try and contact that guy because he had pictures of the larger area. He explained all the algorithms more than all of these links.
Maybe you can get a picture of that from him.
Well, this is the blended picture of 4 different pictures. The better thing is take the 4 pictures, full explanation of how things were figured out, and so the techniques they used, they really did seem reasonable at least one area. The other parts I didn't, we didn't dive into as much detail, and so it was sort of more abstract.
I'm waiting for a Polaroid.
No, this is not a picture. This is a
Well, I'm waiting for a
blended
picture.
analysis, a blended interpretation.
Well, that's why I'm waiting for the picture.
Yeah.
Yeah.
And
Shall we go back to the Model G stuff that we were doing earlier?
Sure.
Okay.
So let me go over the other things that I mentioned in the Facebook. While I still have the screen, at least if I can. No, I should be looking at Model G, not all of this other nonsense stuff. Who knows what comes up on my Facebook page, on my Facebook feed? Who knows? I don't look at it much.
We have a lot of notifications there, huh?
Yeah. I figure, okay, that's from Brendan, or I know I have comments down here somewhere.
Can I make them notice something? I noticed in the emails, it said the meeting was at 8 Greenwich Mean Time. But
Go on.
yeah, but it's now just turning 8 o'clock right now from what I'm seeing on the internet. So
We're talking about the difference between London time and GMT.
oh, there is a difference.
London time is different from GMT in the summer.
Okay.
I did that because Paul got a little bit confused with the GMT, so I just put London time and the other times, the Eastern Daylight Saving and the European summertime.
But you did put the Eastern Daylight Time and at 3 o'clock. So okay, thank you.
Okay, I put that in the email.
You did.
Yeah.
You did. Thank you.
Okay.
All right. So here was my comment, and I mentioned it in our call earlier, that if you copy the MX double for loop that outputs the inside of this, and you turn this, this chart, this chart, and you flip it on its side like this. If you want a whole sequence of these, you can just take that double for loop and you can put it inside the next iteration function. And that will give you all of that data. Of course, you need to take that data and put it into the plot, which I don't know the Octave or GNU plot. I haven't looked at that, so I haven't seen how to do that, but I can do that. This will help visualization, how the soliton forms. Another and then I talk about, hey, could we do another 3D chart similar to some of the stuff that Matt did? And that would be, because what we have here is a chart, okay? What we could do is take this chart and just rotate it around itself.
Yeah.
So then you have a 3D view of this chart, because that's really what the soliton looks like to a certain, from a 2D perspective.
I was thinking of, Justin, I was thinking of just going along with what David said and inputting trying to find out how to input the velocity term into the 1D setup and see what happens with that. So the velocity will be just one-dimensional velocity.
And setting up the initial conditions for velocity is also important.
So velocity omega equals v over r. So v equals r times omega. R would be one-dimensional.
Okay, so maybe I'll work with the 3D views, see if I can get some 3D views out of it, if I have time this week. So those are the two things that I talked about.
Okay.
And then I don't know how to do an animation, but that might be another thing that could be worked out.
Oh, you say that again, Justin?
So I talked about two different types of 3D views we could look at, and then we could sequence the 3D views one after another to create an animation. And supposedly one of the tools you were working with had that. And
I mean, with Octave you can do it, but it's just a question of finding out how to do it. With MATLAB you can do it quite easily because it's very professional software. They show you everything online. With Octave, sometimes you have to create your own functions because it doesn't.
Well, I'm starting to understand this. This Crank Nicholson. As we're getting into more, so I'd probably play with it here. And I'm comfortable playing with this stuff here. So since I've worked with Nuplot before, I feel comfortable working with this.
Okay, so if you stop the screen, Justin, I can show some other screens.
Sure. Stop share.
Okay. So with the I just made a note of this is David Johnson's JavaScript, which he's working on, called Euler Solver, and where is it now?
Yeah, I'm just going to replace the solver with this Crank Nicholson.
Okay, so the Crank Nicholson solver looks very much like these equations. All these, except for the delta, seem to be solved in another in the Crank Nicholson the Crank Nicholson part. So that's one thing I've worked out. So also I showed on here some when I discovered that the Crank Nicholson solver was more sophisticated. It's like a very sophisticated form of trapezoid rule. So these here are like there's this one here, which is a Manchester University maths professor, or mathematics guy, talking about the Crank Nicholson. That might be helpful as an introduction.
Yeah, what I don't know is how to determine the step length. How can we be assured that we have a step length which is neither too small or too big?
When you're talking about step length, David, I assume we're talking about this bit here, this time thing here.
The time, delta t.
There's the x, and there's the time. That bit
there.
Yeah,
the delta t. How is that determined? Now I just took the figure that Matt Palmer had designed, but I don't know how to determine it to make it efficient. The bigger it can be, the faster the algorithm will be, and so on.
I think you have to play with it.
Yeah, but there are some methods to determine because if you make it too big or too small, you lose precision. Especially if it's too big, it becomes too coarse. And
a lot of variables here.
Yeah.
I would just play around with start with a small, do a small size and then larger sizes. If you come across some paper or something which tells you how to get the optimum size, and that may be useful. I came across one paper describing how they used a Nicholson solver in a certain type of physics.
Yes.
So really what I've worked out is that it's more complicated. I was first of all looking at this bit here, and thinking, oh, okay, looks maybe straightforward like the trapezoid. And then I realized, as I investigated it further, I realized it's actually much more sophisticated than that. It's based on the trapezoid rule, like Simpson's rule, but it's much more sophisticated.
Mm-hmm. Yeah.
But Matt's obviously got the code which does it. So another method might be to go into this code here and basically step and work out what he's doing here. Put a comment in here, print out variables, blah blah blah. So work backwards, see what he's done here, work backwards, and try and see how it matches up with this, that kind of thing. So these were other ones. There was another one here which looked quite good. This one here. So this is one I found, which was Cranach-Nicolson scheme. So they go through the theory there, and then they give an example. This is an example of how to solve the heat conduction equation, second order differential equation. And I think this one here this is more paper-like. And this is another one here, which is numerically solving PDEs with Cranach-Nicolson solver. So this is more. This is another approach. So what I found with my work is that my PhD was sometimes reading around what other people say. So you stick where you've got one author saying one thing, you go to another author who said it in a different way, and sometimes that often helps to make it clearer.
Yes.
If you read from different sources, you get different subtleties and better and different.
You know, the big thing here is also to design initial conditions. It's very trivial to do that with the current solver, which has no velocity and only a small disturbance. It's very easy to put that in initially. But if we want to test for different kind of stabilities of different kind of velocity distributions, this work should be done rather soon. Otherwise, I think that's a major task to set that up.
I like setting up. It's like doing a new version of this here. Can you see this? This is the partial differential equation, and you're splitting it up into this kind of thing down here, and we have to do it. We have to sort of do it to incorporate the velocity term.
Okay, the velocity, is it the same velocity for all three components here? I suppose it is.
No, but I thought of it as more like I thought of it more as for x, g, and y velocity for
Do they have one velocity?
You could give them the same velocity to start with and see what it looks like, but you might want to. And that's a good point, David.
Yeah, I mean, we just get the. If we don't know, maybe Paul knows this best. If these concentrations can have a different velocity, or if they are all moving at the same velocity. I guess they are independent.
You mean X, Y, and G? They will have different velocities because they have different diffusion coefficients.
I see.
And different magnitudes.
You may want to adapt the velocity so it relates to. So if you've got the known spin of a subatomic particle,
then we go
the velocities of the ether until they gave the same values of the spin of the known spin of a subatomic particle.
Well, if we
once we get it in 2 dimensions, then the thing is to put 2 gradients, one this way and the other the opposite way on each side of the axis. Try to get the thing
really? You mean you can have motions in the same in the opposite directions, and we need to take both into consideration?
Yeah.
Yeah, that's a big thing. But why can't we just take the net flow instead of both of these?
Because one velocity is happening to one type of etheron, one velocity is happening to another type of etheron. So you've got, here's your space, you've got, this type of etherons which are concentrated over here. One type of etherons are concentrated here, so they're diffusing out from this direction. Here you got another central of this other type of etheron, and it's diffusing out this way.
Well, you don't have to put velocities, just put gradients, because the gradient generates the velocity. right?
Yeah, wait, you lose if you put out in a potential, if you put in a velocity potential that you define that the gradient is the velocity, then you cannot have any rotational velocity based on such a model. You can only have conservative velocities in that case.
So there's a change that happens, even though you've got diffusion in this concentration. When they start reacting, okay, the reactions start causing, so you could have this diffusion, and the diffusion could have a rotational, okay, here we've got a diffusion, and here we've got a vortex for, exons, yons, GNs reacting, particle or what have you that's formed. And we know that particles rotate. So somewhere in there, we have to have some type, the reactions might be reacting in such a way that, you got this exon, this Y-on, a grouping of them, and they react. And then one direction from them, we got two exons coming this way, Y-ons coming in this way, and they hit. And then because there's a specific geometry for how they're reacting, you're going to get a specific angle of reaction coming out. So you add all those angles up, then you're going to get the rotation.
But you might not need to work with all three. Just put your gradient with the G, or your diffusion with the G, because the X and Y follows from the G. So that could propagate to the others. You see what I mean?
But my impression is that we need, like, instead of having one value per component, we need 4 values per component. 1 concentration and 3 velocity.
Well, what I was saying, David, is you could look at the spin of the known spin of a subatomic particle and maybe adjust it to that. Because so the
spin, that's
we don't know what the spin, all they do is they claim it has spin, but they don't, they just make a quantum
but then
number for it.
Put up a spin motion then and put this into the solution and see if it's stable. That's a way to find out if it's possible.
And also measurement theory and observation. So one needs an observation, and then the theory to either adjust the theory so it's the same as the observation. So we need some kind of observational point where we make an observation that infers spin, and then we either adjust our model so that it fits the observation.
Well, if we can just get it to spin, that's the first step, right?
Because it's going to give a value of G, X, and Y gradients. So we know what a subatomic, we know certain properties of subatomic particles. So we just adjust the model till it gives us the correct G gradient, G, X, and Y concentrations for the subatomic particle. If the G, X, and Y don't agree with observation, then we know we need to adjust the model in a different way. Because at the moment, without this, we're just doing this bit here, and we're getting the correct G compared with observation. So if we add this term here, this is going to change. We just need to adjust it so that it gives the correct G, which is consistent with observation.
But you have not included velocity. You have a velocity term there in the end.
Yeah, this term is added. This term I added in there.
Yes.
David.
Yes. Are you only having omega on velocity?
Well, this V velocity term is derived from the omega. So up here, we look up. See down here, it's derived from the omega. So
you mean you have a constant rotation, solid body rotation?
So let's have a look. Can you see here? Omega. That's what omega equals. So this velocity could be is constant, but its direction is changing. So it's
All right.
but very,
So you just have you have like a solid body rotation.
so it may be constant magnitude, but it's differing in position. Its position is different each time at each moment because it's going in a circle.
Uh-huh. Yeah.
So what we need, what I'm thinking is that we need certain observation will show that observation of a subatomic particle. So far, when we took this bit out, we're getting a value of G, X, and Y for a subatomic particle that is consistent with experiment. But in order to get a more accurate value, we're including this term, which is hopefully going to give us more detail at a microscopic level. So
Well, maybe you
we
should
make an
write
observation.
out. Maybe you should write out the differential in equation 40 then, so it becomes clearer.
Sorry, David, say that again.
Yeah, maybe you should replace V omega for the differential term you had higher up.
The omega, this omega, this is just V. This is V. I put the omega there to show that it's angular,
Yeah,
but it's just a V term.
but it's a vector term anyway.
Yeah. Okay. So you're right. It's that. So it's just rearranging that equation where you get V in terms of omega. So if it's just a simple like 1D component, is omega equals V over R. So V equals omega R. So we could put, what we could do is put omega R there.
Okay, but where are the other equations where there are velocity dependencies?
Yeah. So I've just given the example of G. So the other ones, so these ones up here. So these ones up here, you can see that the G I've just added, that there has been added in along with this. So this was here. This is the was derived from up here. So it's derived from up here. So here's the convective flux. Rate of change of so this one here, this concentration here goes into hang on, this R bit here goes in here. That bit there comes from there. So I just said okay. So we before we were just using this piece.
Yes.
So this piece here, you can see down here. You can see that's the R term. That's the reaction term which goes in there. So before we're only using this bit. We were neglecting this. So what I've just done is I've said that's okay in the final component. You can see that term there. There it is. There's the linear term. So I'm saying okay, that's the linear term. Why not just add the convective term? Because these are like vectors of that and that have the same dimensions, like a vector triangle or vector hexagon. So I'm saying let's try. I'm not saying I'm right, but I'm saying I'm making an educated guess. I'm saying let's just add the velocity term to here. That would be that we can see earlier, and then with this one here, we want to add the velocity. We want to add that's the term we're using. We want to add the velocity term. So the velocity term you can see here is the same. This here is the same units as this. It's just like a different you could think of it as a vector of a vector of concentration motion.
Yes.
So this has the same units as this. There's the S there. There's the S there. So before Paul neglected that because he didn't need it. He just needed to do a basic translational motion. And now we're saying let's keep this. Let's add this in there and call that the velocity due to rotation. So then with that one, so what I'm saying is that if we go down here with this, I'm saying with the X term, that's the X one. So now just add the velocity term, similar velocity term, and with the Y, that's the Y version, the linear version. Then just add the velocity term to that. I mean, I don't know if I'm right, but I get a quite a good feeling that I'm on the right tracks. I could be right.
Okay. And what value do you want to put as initial value
Well, I'm just
for?
thinking of putting any. Thinking of putting just give it a value, and if it's one dimensional, then there's omega equals v over r, or
Yeah.
or omega equals dv by dr. So v equals omega dr. That's one dimensional.
Okay.
So maybe just give it a term, give it a value, and then just see what the model produces, and then give it another value until it starts to make more sense and be more, and then align. So what I'm saying also is that these g, x, and y should be relate to experiment, relate to observation. So you're making observation of a subatomic particle or proton or neutron. They must have values of y, g.
What observation are you referring to?
I can't. At the moment, I can't. I'm just trying to think. I'm just being abstract.
These are etheric reactions. Physicists don't accept etheric reactions, and we can't observe the ether. You know, at that level.
Yeah. So what can we observe something that's closer on the quantum level, that's coming from the etheric level?
Well, the spin. They just come up with a spin. It's a vector. So what we're doing is we're creating a model that involves rotation. We're creating a hypothesis that spin is due to etheric rotation around the axis. Right? If we can just show that we've made a step forward. If we can show a dissipative structure that has a vortical motion to it, then we've made a step forward. And then we can figure out about adjusting it later.
Yeah, just to get the model actually working on a kind of abstract level, a basic abstract level. I'm just trying to think of experiments. I was thinking of the I mean, there are experiments using. I'm just thinking of the. I mean, maybe I'm a bit rusty here, but I'm thinking of the double slit experiment. I'm thinking of the Nicholson. I don't know if the Nicholson-Morley experiment will come into it. I mean, what physicists usually do anyway is they make inferences. They infer upon inference. So that if they're observing if they're making a so-called observation of a subatomic particle, they're using machines to infer to another machine, to infer to another, inferring, and then using calculation to
Well, they get a magnetic moment or something from the spin, right? Like they use it in nuclear magnetic resonance.
and also the Stern-Gerlach experiment.
Yes.
Stern-Gerlach. And
Right.
the what should we call it? The what's his name? The Einstein, Rosen, Podolsky. What's it? Alan Aspect's experiment.
I mean the quantum entanglement. You're referring to?
Entanglement, yeah, and Stern-Gerlach as well.
Right.
That's measuring spin. That's for measuring quantum spin.
Okay. Yeah. So we can use the parameters from Stern-Gerlach to adjust it later, maybe. Yeah. You know, what we develop at first probably is not going to be realistic entirely, and then later we can improve. So.
Yeah, so just get the model working so that we have a velocity term that gives a plot that looks roughly in the right ballpark.
Well, the reaction constants, they're already more or less defined from the previous simulations, because you got the neutron and neutrino profiles that match each other. So there's no constants that you have to come up with additional constants here. So I think that would simplify things in terms of pinning down the parameters. I think the constants are already pretty well defined. Yeah.
Yeah, and also one of the thoughts I had was if you look up spin, I'm going to show it straight away.
You know, later we can do experiments with two spins
Yeah.
and see if they can attract each other, and see that's what would create the nuclear force, for example, is the spins entraining one the other, and we could somehow.
What kind of force would that correspond to?
Well, the nuclear force, where in subquantum kinetics, that's due to two ether vortexes going in a compatible way. So they, on the near side, the ether flows are the same direction.
Okay. Yeah, we could just put up, we could have put up initial conditions of these two types and see what's happening if they are attracted or repulsed. Repelling.
Yeah.
Existence of spin angular momentum is inferred from the experiment. So yeah, okay. So angular momentum. So it's using units. It's using the quantum mechanics is measuring it in terms of those units, angular momentum, and then I suppose what we need to do is relate that to the units that we're using and see if there's any similarity.
Yeah, we could say that this amount of spin is equal to this amount of magnetic field creation due to spin. Make an equivalent, something like that, as a starter.
Okay. So the next task is to try and understand the Crank-Nicholson solver, try and get a head around it, and do research in different places and try and understand it properly, because although it's based on the trapezoid rule, it seems it's, as you can see down here, it seems like it can get quite complicated. And so once I understand the Crank-Nicholson method, then I'm going to be in a better position to know what to change in here, in this code, as well as, because I mean, if I just, I mean, last week Michael was saying, why don't you just add it to one of these? Well, if I added the equation, if I tried to add the velocity term to this, I wouldn't necessarily know what I was doing straight away if I haven't understood it fully yet. So it's better to understand how this code relates to the actual.
You might actually be getting larger matrices because you've got more equations in there, more pieces of equations.
It seems like the data requirements are increasing fourfold, aren't they? If you get a velocity component to each etheron.
Can you repeat that, David?
It seems like the data, the volume of data will increase 4 times if we need 3 velocity components for each etheron.
Well, I was going to do it in one dimension to begin with and see what happens. To start off with the simplest.
How can we show spin with one dimension?
Well, I mean, that's a good point, but I was going to just, I was thinking of if you've got omega equals v over r. Yeah, so that's it may just be just like, I mean, you may be right about that. That may not be possible, but I was going to try it anyway because it's along one dimension. What do you think about that, David? You were suggesting. Do you think?
Yeah, you can. I cannot straight away analyze or understand that. I need to find out
two
more. But
dimensions.
it's yeah, it's
Omega equals, it's the rate of omega equals V over R. So if the R is like one dimensional,
yes.
then omega is radians per second. Velocity
But
meter.
R is in the one dimension. It's not
Yeah.
perpendicular to
Yeah.
that dimension.
So that's only including V as a magnitude. It's not including V as a vector in two-dimensional space.
Okay. Yeah.
So V has to be proper. V, if you just put omega V over R, that's just the magnitude. If you want to do it in proper space, that V has to be either two-dimensional vector or a three-dimensional vector. Because omega equals V over R, that's just for magnitude, not for
Well, I think as a starter, we have to do this in two dimensions. Even if you don't put velocities in, we have to first figure out how to do the modeling in two dimensions, right? And then,
yeah, okay. So basically, do all this. See if we can do all this. And David, you seem to be concerned about getting this done quickly. I mean, I'm okay. I can just pace my way through it and build, as Justin was saying earlier this week, just get there little by little. We step towards it little by little.
Yeah.
Because it's
I just don't see currently how this works, but maybe if I think more about it.
I had a strange dream the other night that I related to the work we were doing.
Mhm.
Do you want me to tell it or?
Yeah,
Sure.
we're always interested
I
in
was in a forest, and there was this boat, and I was in the boat, and the boat was buried in the ground, and I was digging away at the front to try and get the boat out of the soil, and there were a few people at the back of the boat who were just watching on and giving advice. And then I was it seemed a bit of a hopeless situation. That the forest is like can't see the forest for the trees. It was like the code and the problems we're facing. I saw the buried boat seemed to be like subquantum kinetics and trying to resurrect it. And then there were several people, rich people in a car watching on, and they seemed to be supporting what we were doing. And then one of the rich people in the car went down a tunnel, and there was a train coming in the opposite direction, and the train pushed his car and scraped the metal on it. And he seemed to be, in the dream, he seemed to be okay with it, because he would do anything to support what we were doing. So I don't know. I didn't know that someone helped me with the interpretation of that dream, but the boat represents.
I do know a rich mathematician. He's supporting our work in Prague for the work on the high voltage research, which would be ether physics that we're doing. So he's a PhD in mathematics, and that's how he made his money, by doing arbitrage in the market. He developed programs to buy and sell. I don't know how much he knows about Crank Nicholson, but I'll be going up to Prague in late May, late this month, into early June, probably. Maybe I'll meet him. I hope to meet him. I can maybe interest him. Maybe he can join the group, if he wants to.
Okay, very interesting.
Get some insight.
So the boat represented the subquantum kinetics, and when I dug it out, when I dug the boat out, which I didn't in the dream stopped before then. The idea was that the boat would carry us towards our destination, which was solving the problem we have at the moment. And
yeah, we got to get the boat out of the mud.
But
it's getting late here, so I'll take off.
Yeah.
So,
Yeah.
continue. sounds like we're making progress.
Okay, great.
Yeah, slowly, piece by piece, maybe. Yeah.
Okay.
Likewise.
Yeah, Brandon, you went over a lot of good stuff, looking at the equations in more detail. So it's been very interesting. And I'm starting to get a better feel for what's going on.
Yeah, and I look forward to be able to contributing more. I was working on a laptop, hoping to get an extra piece of hardware, but it's still broken. So unfortunately, I don't have a spare laptop just yet. But I'm looking forward to having more spare time and helping out more.
Okay, thank you, Michael.
Mm-hmm.
Okay,
night.
so okay. Well, we'll call it. We'll bring it to a close then. Okay.
All right.
Okay.
Bye, Brendan.
Bye,
David.
Justin.
Bye,
David.
Justin.
Michael. Bye then.